Okay, so good morning students, welcome back to this channel. So let us continue this series on Abhyas. Okay, and I welcome you all to this lecture, the third lecture of this Abhyas series, basically on hydrostatic forces on surfaces and buoyancy and flotation. Okay, so these from these two topics we are going to deal some good questions like we have dealt in the previous cases. Okay, like we have already finished two lectures on this course, basically Abhyas course. First lecture on problems on fluid and its properties, second lecture on this pressure and its measurement. Okay, we have seen some nice questions. We have used all the concepts in both the chapters to solve the questions. Okay, so in today's class we will solve these questions on hydrostatic forces plus buoyancy and flotation. So are you all ready? Yeah, good morning all of you. Vikas, how did your HPCL exam go? Good. So please type in the chat box, how did your HPCL examination go on? Good. Yes. Okay, so shall we start? Are you all ready? Shall we start solving these questions on buoyancy and flotation and hydrostatic forces? Shall we revise the things and shall we go? All of you, please type in the chat box. Yes, all of you who is on live, so type in the chat box. Shall we start these questions? Are you all ready? So let us go for the first question right away. So if you see a 7 centimeter diameter solid aluminum ball, specific gravity 2.7. so specific gravity of aluminum is given 2.7. let us write down. So specific gravity of aluminum balls, so specific gravity of aluminum is how much? 2.7. okay, and a solid brass ball of specific gravity 8.5. so specific gravity of this brass is equal to 8.5. now balance nicely when submerged in a liquid. So if you see there is a liquid line here, so you can see this, there is actually a liquid water free surface line here. Okay, so if this is a free surface line, then what they are asking you, this aluminum ball and brass ball are actually balancing the things. Okay, so fluid mechanics itna hard kyun hai? Actually fluid mechanics is one of the very basic sciences. Okay, look, fluid actually, if you understand fluids in a practical way, means if you see the applications of fluids outside, it is very much easy to solve questions on fluid mechanics. For example, you see this question, they have suspended two balls like this, aluminum and brass. These two balls are in fluid. Okay, so what's happening here, when these two balls are submerged in fluid, this balance is in static condition. Means if you see this is in equilibrium, so there is no movement, which means this balls are just hanging this rope tight, that's it. Okay, so if the fluid is water at 20 degrees Celsius, so fluid is basically water at 20 degrees Celsius. So the meaning of this is this fluid is water and this at some normal conditions at 20 degrees. 20 degrees is normal temperatures that we see outside, so 20 degrees Celsius. The diameter of the brass ball is dash mm. Okay, so what about the diameter of the aluminum ball? They have given you 7 centimeters, correct? So when they give you 7 centimeters, then let us calculate what is the dimensions of the brass ball. Now tell me one thing, these two balls are connected by the same string, yes or no? And whenever these two balls are suspended, this string will be in tight condition, correct? So this string will be tight over the balls, which means, can I say one thing, let us suppose if the tension in this string at this location is T and the tension in this string at this location is T, since this is the same string that is passing over, can I say these two tension values are same? Yes or no? So please type in the chat box, can I say this? Since these two strings are connected, of course these two balls are connected by the same string, so in a single given string the tension remains always same. So can I say that the tension in these two strings which is developed here is same? Yes, can I say this? Rohit, Ankush, Vikas, Rohit again, Amit, all of you guys, you should respond. Okay, so if you see, let us draw the free body diagrams of this aluminum and also the brass balls. Okay, so let us take the free body diagram of aluminum ball. This is aluminum ball and let us suppose this is brass ball, for example. Okay, so this is your brass ball. Now if you see, these two are completely submerged in fluids, so definitely this aluminum has some weight, which is weight of the aluminum. And since this fluid is completely submerged inside since this ball is completely submerged inside the fluid, we have a buoyancy force which is acting on this. Okay, so this is F buoyancy acting in aluminum. So buoyancy force FB on aluminum. And also if you see, there is also the tension force. So if you see, there is certain tension by the string. Okay, so tension by the string is also there, so this is T value actually. So this is T and this ball has weight and of course buoyancy force and the string has some tension. So sorry, excuse me. So if you see, this is water at 20 degrees Celsius. Similarly, if you offer this brass ball, so now what you have, this weight of the ball is acting in the downward direction, which is actually weight of the brass ball. Next, buoyancy on this is actually acting on the topward direction. So F buoyancy on this bus, and of course you have this tension. So you have this tension also. Okay, so let us see tension force T. Now under these force conditions, these two balls are in equilibrium. So let us take care of this particular ball. So if you draw a free body diagram, since this ball is stationary, we can write T minus or T plus force acting on the aluminum due to buoyancy is equal to weight of the aluminum ball. Similarly, from that free body diagram, we can write T plus F buoyancy acting on the brass ball is equal to weight of the brass ball. That's it. Okay, so these are the two things that we can write. Okay, 42.68 centimeters, 4.27 centimeters. We'll see what is in. Okay, you wrote in mm. Okay, let us check the values. We'll take gate calculator, we'll solve the question. So if you see, tension in both the cases is same because the string is uniform throughout, which means you have weight of aluminum minus buoyancy force acting on aluminum. This is equal to weight of the brass ball minus buoyancy force acting on the brass ball. Okay, so if you simplify the things, now what is weight? These are balls actually, so they are spheres. If they have a diameter d, then let us suppose if the diameter of this is d aluminum, and let us suppose the diameter of this is d brass, then if you see, this fluid is completely submerged inside this aluminum, so you can write density of aluminum minus density of fluid, which is water, times pi d cube by 6 into g. So this value is equal to density of brass minus density of water, because the fluid is water, times pi by 6 times, let us make some small correction here, let us write this value as pi by 6 d aluminum cube. Okay, because you know this is the diameter of the aluminum. Similarly here, diameter of the brass whole cube into g. So let us cancel the common terms. G gets cancelled on both the sides, pi by 6 gets cancelled on both the sides, which means you can write one thing, the diameter of the brass ball is equal to diameter of the aluminum ball into this values. If you see, density of aluminum minus density of water divided by density of brass minus density of water whole to the power 1 by 3. This is the value. So this is the dimensionless quantity, and you have these dimensions. So looking at the dimensions, what they are asking you, you will substitute this DAL value. But densities are not directly given. So what we can do, we can take density of water common in both the terms and cancel. So if you take this common, what we'll have, density of aluminum times, if you take density of water out, we have density of water into density of aluminum by density of water, which is nothing but specific gravity of aluminum, minus 1. This value divided with density of water times, similarly here, specific gravity of this brass ball, minus 1. So this is the value whole to the power 1 by 3. So anyhow, this density of water gets cancelled out, and if we need 3 values to evaluate this equation, we have all the 3 values. Okay, so specific gravity of aluminum is given to you, specific gravity of brass is also given to you, diameter of aluminum is also given to you. So this implies d brass is equal to, let us see what are the units they are asking you in. They want the diameter in mm, but what is the diameter they have given you here? It is in 7 centimeters. So let us substitute in mm. So 70 times. Now, what is specific gravity of aluminum? 2.7. So 2.7 minus 1, which is 1.7 by, next, specific gravity of brass is given 8.5. So 8.5 minus 1, which is 7.5 whole to the power 1 by 3. So this is the value of diameter of the brass in mm. So let us quickly take the calculator and let us punch some keys to get the answer. Let us open a virtual calculator. Okay, so gate calculator. So if you open this gate calculator, we have this. So 1.7 by 7.5, 1.7 by 7.5. So this value whole to the power 1 by 3. So 1 divided by 3. So this value you have multiplied with 70. So multiplied with 70. So if you multiply this, 42.68 mm. Okay, so 42.68 mm actually. So diameter of the brass ball is equal to 42.68 mm. It's a very simple question. Basically, to balance the weights on both sides, we need to balance this tensions. That's it. Okay, it's very good. I'm very happy that all of you got correct answers. 42.68 mm. Rohit, they have asked in centimeter, I mean this mm, so that's why we have converted that 4.268 to 42.68 mm. Okay, so it's a simple equation. You can see we haven't done anything. Some small calculation, 3 values are needed, all the 3 values are given, so you can calculate this. 42.68 is the correct answer. So 41.5 to 43.5 is within the value, so 2 decimal places, so you can round off to 42.68 mm. Okay, clear? Yes, right, correct. Bhavya. Okay, yeah, Bhavya. So correct, got it. It's a very simple question, right? But it's a good question. Good to see that 2 spheres are hanging in water and all these things. Clear? Now let us see one more question. Okay, so second question: a curved face of a dam which is shaped according to the relation y is equal to x square by 9. So if you see, this is the horizon, then how this y is changing, y, and if this is your x-axis, they have told that y is equal to x square by 9 parabola. So this shape of the dam is given by y is equal to x square by 9. The height of the water retained by the dam is 10 meters. So 10 meters height of the water is actually retained. Consider the width of the dam as unity, means into the plane of the board the width of the dam is actually 1 unit. The magnitude of resultant water pressure force acting on the curved face is dash. So this is the curved face. So this is basically hydrostatic force acting on the curved face. Okay, so how we will calculate this? Look, let us try to solve this. So basically, if you see, this is your x-axis, this is your x-axis, and this is your y-axis, for example. Okay, so this is your y-axis, origin x, y, and let us suppose the dam is something like this. This is the dam. Okay, so this is y is equal to x square by 9. Okay, so y is equal to x square by 9, and of course you have some fluid like this. The height of the fluid is how much? 10 meters, correct? So if you see, the height of the fluid is actually 10 meters. So the height of the fluid is 10 meters. Okay, so this height of the fluid is basically 10 meters. 10 meters. Now if this is 10 meters, now let us see what is the hydrostatic force acting on x direction and also on y direction. So how will you calculate this? So we know Fh means Fx, if you take F horizontal force acting in the x direction is equal to density of the fluid times gravity into area of projection of curved surface onto yz plane. Let us say onto yz plane, because yz plane is the plane perpendicular to x-axis. Okay, so basically if you want a force in a particular horizontal direction, you need to project this area, curved area, onto a plane which is perpendicular. So let us take the z direction, something like this. So let us suppose this is the z direction, for example. Okay, so this is the z direction. Okay, the third dimension into the plane of the board. So multiplied with depth of centroid of projected area from free surface, correct? So from free surface. Okay, so from free surface. So basically how you will actually project this? Look, if you take a projection, means if you see the side view of this curved surface, the side view of the curved surface looks like this. The side view of the curved surface looks like this. It looks like, can you tell me one thing before I proceed? If you project a curve onto a perpendicular plane, what is the geometry you will see? If this is a curve and if you are projecting this curve onto a plane, means if you are seeing the side view, can you tell me what is the geometry of this curve that you will see? Can you tell me what is the geometry of the curve that you will see from the side view if you project it onto a plane? All of you. Yeah, of course, the surface is rectangular, the curve is a straight line, correct? Means if you see there is some curved surface like this, so if you see this curved surface projection on the side view, you will get a rectangle like this. Okay, so this is a rectangle. So you know this height is known to you. This is 10 meters, and this is 1 meter, because they have asked assume unit width into the surface. So this is a rectangle. So where does the centroid of the rectangle lie? Exactly at this point. Okay, G. And what is this from the free surface? This is 5 meters. Okay, so this is 5 meters. So 5 meters G we have. So if you see, this value is equal to This implies Fh is equal to density of the fluid times G into area 10 into 1 into depth of free surface, depth of centroid from the free surface. Total, this is 50 times of density of the fluid into G. These many newtons. Okay. Next, coming to Fv. Fv is nothing but what is the vertical force acting on the dam actually. So if you talk about the vertical force acting on the dam, this is nothing but the weight of this fluid which is supported by the dam, correct? Means if you take this curved surface, what is the weight of the fluid that is supported by this dam is actually equal to the Fz value. So Fv means basically Fv in the vertical direction. So Fv is equal to weight of the fluid supported by dam. Weight of the fluid supported by dam. Weight of the fluid supported by dam actually. Okay, so this is Fv. So if this is weight of the fluid supported by dam, so this is equal to density of the fluid times gravity into volume of the fluid. So volume of the fluid can be written in this way. It is of 1 unit thickness. So 1 unit into, let us suppose if I shade this area, for example, if I shade this area and if I call this area capital A, then this is nothing but 1 into capital A. Yes or no? So please type in the chat box. Are you all clear till here? If you are clear, then we'll see how to calculate the integration and all. But are you all clear till this point? Because Fv, vertical force acting on the body, on the surface actually is nothing but the weight of the fluid which is supported by this curved surface. Okay, so the weight of the fluid which is supported by this curved surface, okay, clear? So is equal to this value. So how will you calculate this area? Let us go for some simple integration. You know, this is y-axis, this is x-axis. You have a curve like this. You have a curve like this. This is y is equal to x square by 9. So if you want this area, then this dimension is 10 meters. This dimension is 10 meters. Then in that case, if you want the area, so you take a horizontal strip, for example. So if you take a horizontal strip, so this dimension is dy, and let us suppose this is x. So dA, small dA is equal to, means this elemental area is x times of dy because it is rectangle. So x into dy. So what is the total area? A is equal to integral y is equal to 0 to y is equal to 10. What is x basically? X value at any location is given by this function. So x is equal to 3 times of root y. Okay, so x is equal to 3 times of square root of y. So if you replace here 3 times of y power 1 by 2 dy. Okay, so if you simplify this, this gives you a is equal to integration of y power 1 by 2 is 2 by 3 times of y power 3 by 2. So this is total 2 times of y to the power 3 by 2 from limits 0 to 10. So this is 2 times of 10 to the power 3 by 2 meter square. This is the area actually. Okay, so 2 into 10 to the power 3 by 2. So we have this is equal to density of water times g into 1 into that value, which is 2 into 10 to the power 3 by 2. This is the value in newtons. Okay, so this much value you have. Mehta, you have a question sir? First vertex का वो I'll tell you. For volume spilled वाले questions consider करोगे ना future में वो hard है बहुत. At this end of the lecture, if there is some time, definitely I'll talk about that. Forced vertex flows, water spilling. Okay, no issues. Clear? Okay, Mehta, don't worry. So now if you see this, let us calculate the values quickly. So anything given about the density of the water, nothing is given, so let us take 1000 by default. Okay, so density of water is equal to 10 cube kg per meter cube. Okay, and gravity is also nothing is mentioned, so 9.81 meters per second square. We can take these two values. So let us calculate these values, and finally they are asking you the answer in kilonewtons. So let us suppose if I take this as 10 cube, then this can be written as 50 times of acceleration due to gravity kilonewtons. And if I take this as 10 cube, for example, then this can be written as 2 into 10 to the power 3 by 2 times g, these many kilonewtons. Okay, because this 10 cube we are converting to this kilo, that's it. Okay, so let us calculate these two values. So if you calculate fx, fh and fv, then net force acting is equal to root of fh square plus fv square. Okay, so this is fh square plus fv square. Okay, so let us calculate. If you get this fh and fv values, you can use them and you can get the equations. Okay, so fh 50 times of g, so 50 times of 9.81. so if you simplify 490.5 kilonewtons. Next, coming to this value, 2 into 10 to the power 3 by 2, 2 into 10 power 3 by 2 is 1.5. This value multiplied with g, 9.81. So 620.438. 0.438 kilonewtons. Okay, so this is in kilonewtons. Now if this is in kilonewtons, then square of this plus what is this FH value? We got 490.5. So 490.5 square. Okay, so if you calculate this value, this is the case, square root 790.9074. So 790.907 kilonewtons. This is in kilonewtons. Okay, so this is the total hydrostatic force which is acting on this curved surface in which the dam is of a shape y is equal to x square by 9. Clear? सब ओके वैल्यू लेने में प्रॉब्लम होता है यूनिट की वजह से, प्लीज क्लियर कर दीजिए. लुक, आई विल टेल यू basically what we are doing, we are taking this density value 10,000, correct? Let us suppose if you multiply this 10 cube here, you will get the answer in newtons. So what we are doing, we are eliminating this 10 cube and writing kilonewtons directly. That's it. Yes, 790.907 is correct. Whoever got 790.907, it's correct. Yes, you have done good. Okay, Amit, did you understand one thing? This 10 cube, whenever this density is given, when you multiply density, let us suppose this answer is in newtons, then if you multiply 10 cube here, you will get this value in newtons. So that one 10 cube we are eliminating for writing the answer in kilonewtons actually. Okay, that's it. Clear? Yes, in water 1 gram per cc, you know, sometimes when they give you in cc and all, you need to convert it that into SI units, kg per meter cube. Okay, sometimes what they give you, kg 1 gram per cc is basically equal to 10 cube kg per meter cube. Okay, because you see, if you see the conversion, 1 gram is equal to 10 to the power minus 3 kgs and 1 cc cubic centimeter is nothing but 10 power minus 6 meter cube. So if you simplify, you will get a 10 cube onto the top. Okay, so that's why sometimes they give density of water as 1 gram per cc just to you know, make you to calculate this in SI units. That's it. But now it's a simple thing, you need to calculate the integration for getting this area. So the total force, hydrostatic force acted by the fluid on this plate is 790.9 kilonewtons actually. Okay, Newton में unit हो, Newton, maybe they will give you some mass. Okay, that's it. Whenever they give you in newtons, 1 newton is equal to 9.81, you know, mg. If you take for example 9.81 newton is equal to 1 kg mass actually. Okay, so if volume is known to you, you can calculate density directly. Look, so this is how we get this question, 790.91. Okay, so B is the correct answer for this case. It's a nice question actually. Okay, 790.91. Okay, fine. Acha, maybe yes, Bhavya has correctly guessed it, I think. Look, Amit, sometimes you may see this value as kilonewton per meter cube or newton per meter cube. They give you these kind of values. Okay, this is nothing but density times specific gravity. Okay, then they are giving you rho g value. Then you need not multiply rho and g separately. In place of this multiplication, you can substitute that value which is given in newton per meter cube directly. Okay, maybe you're talking about specific weight, but if they are talking about specific weight is nothing but weight per unit volume. So if you see, this is nothing but weight per unit volume, so you can substitute directly there. Clear? So shall we go for the next question? Are you all liking the questions? Okay, let's go to the third question. The 280 kgs 6 meters wide rectangular gate shown in figure is hinged at location B. So this is location B, this is location B, and it is hinged at this location. Okay, and leans against the floor at A, making an angle of 45 degrees. So this is the angle at which it is made, which is 45 degrees. The gate is to be opened from its lower edge by applying a normal force at its center. So what they are doing, look here, this is a gate. So one thing that happens is, because of this water, there is some hydrostatic force acting on this gate in this normal direction, say something like this for example. Okay, so somewhere here there is some normal force acting on the gate. So to open the gate, what they are doing from this lower end, they are applying a force F from this midpoint. Okay, so this is the midpoint, which means centered of this you can say centered of this plate, basically because it's midpoint. Now the minimum force F required to open the water gate is dash kilonewtons, round off to some decimal places. Did you all understand the question? First of all, physics, what's happening here? The physics that's happening here is, because of the hydrostatic force, the plate is being pushed onto the bottom, correct, about this hinge. Now in order to open the gate, what we are doing, we are actually applying a force F normal to this gate. Okay, so obviously what happens when this force exceeds this water force, then definitely this gate will open at this location, correct? So this is what you have. Now let us convert this physics into some mathematics. Okay, so see here, let us try to convert that. First of all, you have a gate like this. Okay, so this is the gate. Now let us calculate what are the forces acting on this gate. First of all, if this is the hinge B on this gate, and let us suppose this F hydrostatic force is acting, for example, normal to the plate. F hydrostatic force is acting normal to the plate. Okay, this is acting normal to the plate, and if this angle is theta, for example, or this angle is 45 degrees, it is given. So this angle is also 45. Which angle? This angle with the horizontal is also 45 degrees. Now this is hydrostatic force FH, normal to the plate, and also there is one more force which is acting in order to open the gate, that is in this direction to the centroid. Okay, so this is also normal, so this is also normal, and this is acting at this location, which is center, which is G. Actually this is G and this is F, for example. Okay, and one very important thing, the free surface is not at this level, but it is at some higher level. So this is the free surface of the fluid. Okay, so the free surface of the fluid is actually here. So whenever the free surface of the fluid is here, moment concept is also required here. Yes, of course, we need to take look, because the plate is rotating about this hinge, means the about this hinge, this plate can actually oscillate. Okay, so that's why if you see this 45 degrees. Now let us calculate, let us first of all understand the physics. If this is the point of rotation, then let us suppose if I define this length, this, since this is normal, so let us suppose if I take some line passing through this like this, if some line is passing through this normal to the plate, this line is perpendicular to the plate. So let us suppose if, for example, I know this length, for example, I know this length, let us suppose if I know this length as A. Okay, so let us suppose if I know this length as A, and this length, let us suppose I know, let us suppose if it is B. Let us suppose if this length is B, for example. Now if this length is A and if this length is B, then if these are the only two forces which are acting, and of course weight of the plate is also there, I'm sorry, so weight of the plate is also there, weight is also acting to the centroid. Okay, so this is W. So what we will do, because we don't know what is the perpendicular distance between this vertical line and this line, we will resolve the weight into two components, and you know, if this is theta, we can resolve it in this direction, W sin theta in this direction and W cos theta in the reverse direction. Okay, so these are the two cases. So one case is F, which is actually applied at this location. So this W we are replacing with W sin theta and W cos theta. These are the components. This W cos theta is in the downward direction. Okay, so because weight of the plate is also given, some 280 kgs plate is it, so that's why we have this. So this plate is in equilibrium condition under these three forces. One is the hydrostatic force, one is the force which is applied, and this weight force. Okay, now at the point of rotation, means just when you applied enough amount of force just for the rotation of the plate to begin about this point B, then means if this point, this is the point A, for losing this point of contact at this location, you see, for losing this point of contact at this location, this beam has to slightly rotate about this point B. So by the time just the rotation starts, you know, at that equilibrium condition, some of the moments of all these forces with respect to B should be 0, correct, because the rotation is about this point B. So sum of moments about B, let us take anti-clockwise direction to be positive, is equal to 0. So this is what you have. So sum of moments of this about this point B should be 0 here. So let us see what are the counterclockwise moments and clockwise moments. So counterclockwise moments, this FH is counterclockwise and this is perpendicular distance, so FH into A, FH into A. Next, this W cos theta is also counterclockwise, so plus W cos theta into B, W cos theta into B actually here. And of course at the hinge you have certain reactions, Rx and Ry, let us suppose Rx and Ry are the reactions at the hinge, because if you are drawing the free body diagram, you are separating the hinge at that point, so hinge reactions are also there. Okay, so this is W cos theta, W sin theta, so W cos theta into B, and this F is actually producing a clockwise moment, so minus F times of B is equal to 0. This is what you have here. Okay, so this is the equation, and of course you have one more important component, this W sin theta, but this W sin theta line of action is passing through the hinge, so this is passing through the moment arm, so that's why if you see this about this moment arm, this W sin theta don't have any moment. Similarly, these two reactions are also passing through this hinge, so no moments about them. Okay, so this is the equation. So from this equation, if you write expression for F is equal to Fh times of A by B plus W cos theta. This is what you have for the expression. So in this expression, what are the quantities you should know? So this is the expression for the calculation of the hydrostatic, this force F which you are applying. Now if you see, W is given, weight of the plate is given, mass is given. So we need to calculate three quantities, A, B and Fh. Now tell me one thing, if this is a plate of length L, can you tell me what is this length actually, which is this B? Can you tell me if this total plate is of length L? So what is this length L? It is given? Okay, it is not given, but let us suppose if this length is known. Okay, so if this total length is known, then can you tell me what is the value of this B? What is the value of this B? Please tell me, what is the value of this B? All of you, L by 2, correct? It is half of the length because this is centroid value, L by 2. Okay, so let us calculate Fh and A values. So hydrostatic force, Fh calculation. Hydrostatic force is how much? Hydrostatic force acting at this point is equal to, hydrostatic force acting on the plate is how much? Let us suppose if the depth of centroid from the free surface, from this free surface, if the depth of centroid is h bar, then this Fh is actually given by density of fluid times G times area of the plate into this h bar, correct? This is the hydrostatic force acting on the plate. So G A h bar is density of the fluid, G, what is the area of the plate? Look, this length of the plate. So if this is 3, this height is 3 meters and this is 45 degrees. So this slant height is nothing but 3 times of square root of 2, correct? Yes or no? Because this is 3, so this angle is 45. So from this triangle, if you take sin theta, you will get this value as 3 times of square root of 2. Okay, so let us write that 3 times of square root of 2 into, what is the width of the plate? It's clearly given, it is 6 meters wide. Okay, so 6 meters is the width of the plate. So you have 6 multiplied with depth of centroid from the free surface. So from the free surface, which is here, can you tell me what is this depth? This is exactly half, yes or no? Means if you see this total height is 3 meters, then this height is 1.5 plus 0.5. So total this h bar value, depth of the centroid from free surface is 2 meters. Yes, because if you see this total length is 3, so exactly to half location you have 1.5 plus 0.5 meters water head again. So 0.5 plus 1.5, total 2 meters is the depth of centroid here. Okay, so this is the hydrostatic force that is acting. This is acting. Now what about the hydrostatic, what about the center of pressure? Means if you take this value, this value is nothing but your center of pressure. Okay, so this is your center of pressure, H star, center of pressure H star. So let us see what is this H star value. How will you calculate this H star? H star is equal to H bar plus, if you take a projection of this plate, means if you take this projection of this plate, what you will get? You will get a rectangle like this, correct? You will get some rectangle like this. Okay, so you will get some rectangle like this in the side view. Okay, so you will get this rectangle like this in the side view. Now if you take this rectangle, then definitely this is the centroidal axis. So what is the axis of this rectangle about this moment of inertia of this plane about this axis? So please tell me, this is IXXG. So about this axis, the moment of inertia of this plane is nothing but, this is 6 meters wide and this is some value which is 302. So this is 302. So if what is the moment of inertia? This is a rectangle, so B d cube by 12. So H star plus IXX, let us write about the centroid, sin square theta by A into H bar. This is the depth, this is the value of H star, correct? So if you simplify, H star value, depth of centroid from the free surface is 2, so H star value is 2 plus moment of inertia, which is 6 into 3 root 2 whole cube by 12 into area. So what about area? We have just seen 3 root 2 into 6, so 6 into 3 times of square root of 2 into H bar, which is 2, into sin square theta is also there. So what is the value of sin square theta? Theta is 45, so sin square theta is 1 by 2. Okay, so this is the value that you have here. So if you simplify this, 6 gets cancelled, this 3 root 2 cancels this square times, this 2 cancels this root 2 square, so total you have 9 by 12 into 2, so 2 plus you have 3 square here, so 9 by 24. 9 by 24 is what you have. So if you simplify 3 table, 3 8, so 2 plus 3 by 8, so 2.375, correct? So 2 plus 3 by 8, 3 by 8 is 0.375, so 2.375 meters is the depth of centroid. Means this value of h star is actually 2.375. so if this is 2.375, then what is the slant height basically for this triangle? 2.375 divided by square root of 2. So from that you need to take this value actually. Okay, so let us see how it comes out. Okay, so let us take one more slide. So see here, basically h star value, just a second, h star value is equal to 2.375 meters, correct? Now try to understand one thing. You have your plate like this, this is the water surface. Now this is the location of center of pressure, so you know this height, which height? This to this point. Okay, so you have calculated this height, which is h star. If this is h star and if this is 0.5, this is 0.5 meters, then can I say this distance is nothing but h star minus 0.5 meters? I can say this. Okay, so this distance is h star minus 0.5 meters. So you know this angle is theta, so if you see, this value is nothing but h star minus 0.5 times of square root of 2, because this is 45 degrees. If this is 45 degrees, then this is h star minus 0.5, then this dimension, which is here from this location to here, this point. Okay, so this is h star minus 0.5 times of square root of 2 actually. Okay, so if you substitute, which means A value is equal to h star minus 0.5 times of square root of 2 meters, this many meters. Of course B is how much? B is actually half of this length. Means if you see, this is B, this is half of the length, so total length is 3 root 2, so this is 1.5 times of square root of 2. This is the length of B. And what about FH? FH calculation is also there. FH is how much? Density of fluid times G, density of fluid times G into 6 into 3 root 2 times 2. This is what you have here. Okay, so now you got A value, B value and FH value. So if you simplify this, what you have, this let us suppose the answer is in kilonewtons. So okay, let us convert in newtons only, no issue. So 10 cube 9.81, 6 into 3 root 2 into 2, these many newtons. Okay, this is in newtons. So let us calculate this value quickly. Okay, so if you calculate this value, 9.81 into 6 into 2, 12 times of 3 root 2, so 12 times of 3 into root 2. Okay, so this is what you have, 499.44. so 499.44 into 10 cube, 500 newtons almost, into 10 cube newtons. So we have this equation, F is equal to FH times of A by B plus W cos theta, correct? This is what you have here. Okay, so if you simplify this, FH 499.44 into 10 cube into A by B. So what is the value of A? 2.375 minus 0.5, so 1.875. so 1.875 times of square root of 2 divided by B. B is how much? 1.5 times of square root of 2 plus W. So what is W? Weight of the plate, it's given. The plate is actually 280 kgs. If the plate is 280 kgs, then this value is 280 into 9.81. So this is the weight, and into cos theta, so which is 1 by square root of 2. Okay, so W into cos theta is there here. So you have seen in this equation we have W cos theta, so W into cos theta, this is the value. So if you simplify, let us see what is the answer. Square root of 2 and square root of 2 gets cancelled. So if you simplify this, let us see. Finally the answer is in kilonewtons, right? Okay, first of all let us calculate in newtons. So 499.44 into 1.875 by 1.5 into 1.875 by 1.5. So if you simplify this, 624.3 into 10 cube, this is in newtons, plus coming to this value 280 times of 9.81 divided by square root of 2. So if you simplify this, 1942.28, 1942.28, this total value is in newtons actually. So if you simplify this, plus 624 300 almost. Okay, so if you see 626 point something newtons. Okay, so this, if you add in kilonewtons, 626.24 kilonewtons is what you have here. Okay, so this is the force which you have to apply at the center of the hinge, at the center of the plate, so this plate can rotate. 626.24, and if you see the answer, 626.2 something is in between this 624 to 628. Clear? Did you all understand this question? It's very simple. First of all, you understand the physics that's happening here. So once you understand the physics that's happening, we have converted this into some equation. So F is equal to FH. Now next point of interest is calculation of this FH, calculation of this AB value. So FH we have calculated, A value needs H star, so we have calculated this H star value, and this B also. So this question involves this calculations of hydrostatic forces. So that's why we have done all this analysis. Clear? Yes or no? So please type in the chat box. Is this clear to all of you? Yes, 626. 626. I think 624.3 is basically this value of hydrostatic. This, what do you say? The moment due to this value. 624.3 is this value. Okay. So 624.3 is this. So to that you have some weight of the substance as well. Okay. Clear? It's a nice question, correct? Yes, plus the weight should be added, correct? So did you all like this question? It's a good question actually. Okay, so we have to calculate these moments and calculation of these hydrostatic forces, because free surface is not matching with the hinge. The free surface is slightly above the hinge actually. Okay, so clear? Yes. So let's go for the next question. So this is a good question actually. Okay, we have seen some nice understanding of engineering mechanics and also this fluid mechanics. Basically, of course, fluid mechanics is part of engineering mechanics, but still this hydrostatic forces, center of forces calculations, these things are very much important actually in this case. Next, so see, there is a question here. The minimum apex angle of a solid cone of specific gravity is 0.8, so that it can float in stable equilibrium in fresh water with its axis vertical and vertex downwards. So first of all, tell me, in case of this is a floating body, a cone is floating actually, it's given the cone, it can float in stable equilibrium. So tell me, for floating bodies, what is stable equilibrium? What is stable equilibrium actually, if you see? So please type in the chat box, what is stable equilibrium? Anyone, all of you. So please type in the chat box, what is actually a stable equilibrium? Tell me. Tell me, what is stable equilibrium? What do you understand by stable equilibrium? Meta center above CG. Okay, meta center's concept and all. Okay, fine. So basically, stable equilibrium is that position or that configuration of equilibrium when you slightly disturb the position of the body from its equilibrium. The body again tries to come back to the same equilibrium condition. Means, let us suppose, for example, you have a bowl kind of thing. Okay, in this you have a ball, for example, some spherical ball which got settled here. Now let us suppose if you slightly disturb this ball, what happens? This ball again comes and occupies the same position. Okay, so that's how stable equilibriums are those equilibriums where even if you disturb the body, then the body will again try to come back to the same location. Okay, so that's stable equilibrium. So in fluid mechanics concepts, we talk about one very important point which is called the meta center. Okay, no, B above G is not valid for floating bodies because if you see, B and G relations can be valid only for completely submerged bodies. Okay, for completely submerged bodies, but in case of floating bodies, you have some concept which is called meta center, and this meta center should be above this center of gravity. Okay, for the bodies to be in stable equilibrium. We'll see how. Okay, shall we see how that happens? Okay, let us spend some 2-3 minutes time in understanding. Okay, so see here, I'll explain you how it can happen. So see here, let us suppose if there is some body which is submerged in a big fluid. Okay, so let us suppose there is some fluid. Okay, there is some fluid. So in this fluid, let us suppose you have certain body, for example. Okay, we have certain body. We'll draw this body, for example. So you have some body like this. This is some body. Okay, this is completely submerged case. Completely submerged. Now let us suppose this body is actually straight, but we have given some external disturbance. Means normally when the submarines and all are traveling, let us suppose they got some when a submarine is moving like this, where it is completely submerged inside the fluid. So when a submarine is moving like this, let us suppose by some disturbance of wave or something, the submarine got tilted like this slightly. Okay, then again if it is in stable equilibrium, the submarine should again come back to the same orientation, correct? So let us see one such case of a completely submerged body. Now if you see, this is the axis of the body. This is the axis of the body. So if this is the axis of the body, then let us suppose we have this G here and B here, center of buoyancy here. So when this body is in submerged condition, definitely weight acting on the body should be equal to the total buoyancy force acting on the body, obviously. Okay, so weight and buoyancy force should be same. So if you see, weight will be acting in the downward direction and W will be this buoyancy force will be acting in the upward direction. Okay, buoyancy always acts up in the fluid, so this is buoyancy force FB. Now tell me, if the moment which you have applied on this body is in this direction, in the clockwise sense M, then if in order to keep this body in counter position, means let us suppose initially the body is straight, you have applied some clockwise movement, some disturbing movement M, so that this body which is initially like this got tilted. Now if this tilt has to be made vertical again, the moment generated by these two forces should be in anti-clockwise direction, which is the case when G is actually below B. Okay, so if you see, whenever you are trying to apply certain disturbance moment, the moment due to these two forces should be in anti-clockwise direction in order to keep this body straight. Okay, so that's why G should lie always below B. That's why if you see submarines and all, normally how many of you visited submarines? I don't know, but normally if you come to Visakhapatnam, there's a big submarine, the 1971 war submarine, which is kept actually. Okay, so if you go to the submarine, you will find one thing. Normally in Ghazi movie, Ghazi attack, in all these movies you can find, normally in a submarine, if you take a submarine, the engine rooms and heavy compartments all will be at the bottom. Okay, because obviously if this is a body, let us suppose if I fill this portion with heavy mass, and this, let us suppose if there is some less mass in this case, now definitely this centroid will try to come to down below the second half. So that's the reason why, because the bodies in this case should have centroid as much as bottom as possible. So that's why if you see, these bodies are called bottom heavy bodies. Okay, and that's the reason why in submarine all the engine rooms, compartments, all these will be in the bottom column, so that the weight of the submarine is actually more in the bottom part, so that the centroid will actually come down, so that the centroid will maintain a stable equilibrium. This is the case of completely submerged bodies. But in case of floating bodies, these conditions of B and G are not sufficient. Okay, so that's why we come for a concept called meta center actually. Okay, so we have seen, if you see, what is the meta center concept actually? Okay, then don't ask me, sir, why in ship engines are on the top. You won't submerge the ship. Okay, you will float the ship. Okay, submerging the ship is not that good always. So this is completely submerged. Now if you see, let us suppose again you have certain fluid. Okay, so first of all, let me draw. So let us suppose this is the case of a ship. This is the body axis. So if this is the body axis, then this centroid can be here, center of buoyancy can be here, but definitely means basically this is B in this straight location. So now the center of buoyancy will shift somewhere here, because some excess volume is getting submerged like this. Okay, and the level of free water surface is somewhere here. Okay, so let us suppose the free water surface is somewhere here. So this is the free water surface, this is the free water surface. Now if you see, the gravity is in this direction, the weight and the buoyancy force is in this direction. Okay, so this is W and FB, buoyancy force. Now meta center is nothing but the point of intersection of this line with this axis of the ship. Okay, and this M is the point about which this body will actually rotate. Okay, so this concept M is called meta center. And now if you see, if I apply an external moment M on this body and tilt it, then the momentum generated due to these two should try to rotate it again in the counterclockwise. Okay, so this can happen only when this point B dash is towards the right side of this vertical line, correct? This moment will be in anti-clockwise direction for this configuration when this B dash lies to the right side of this G. So that's why if you see, this counterclock moment is possible only when this B dash is lying to the right side of this line, and whenever this point is lying right side of this line, definitely this point M will lie above this G. Okay, from geometry you can see. So that's why meta center concept came here. So M should be on top of G. And how you calculate this? On top of G actually here. And how you calculate this metacentric height? This GM has to be greater than 0 for stable equilibrium, which you know. For stable equilibrium, of course, for stable equilibrium, you know this. So if this is the case of stable equilibrium, then how you actually do the things? GM value is nothing but, you know, there is something called metacentric radius minus BG value. BG is the distance between center of the body and center of buoyancy. Okay, so now if you see, GM is equal to BM minus BG. Clear? So BM is nothing but moment of inertia of the plane about this axis. Means if you see, let us suppose whenever the ship is like this in horizontal form, let us suppose if something like this, if this is the surface, then this is called waterline, the point of intersection of liquid with the solid. So now if you see about this axis, if you see the top view, you will get some figure. So the moment of inertia about this centroidal axis like this, okay, about this point. So this is I by V minus BG. Okay, so this is what you have here. So this is metacenter. Okay, C guy Gareka, sorry, is any information about Gatopedia? Very soon you will get, because everything is ready from our side. So within few days you will get to know of it. Okay, with not more than a 1 week time. Okay, so now let us see here. If you come to this case, now you have a cone body, cone like this. Okay, this is a cone. So this is a cone. Okay, so this is a cone like this. So now what's happening to this cone? This cone is floating on water. This cone is floating on water like this. Okay, so now this cone is floating on water. So if this cone is floating on water, this is the free surface, then this total diameter of the cone is given. Okay, nothing is given, fine. Okay, no issues. If this is the total diameter D of the cone, and if this is the total height H of the cone, okay, so this is the total height H of the cone. Now let us suppose small h portion is submerged in the cone, submerged in the fluid. Small h portion is submerged in the fluid. Okay, and let us suppose at this location the diameter value is small d, for example. Okay, so the diameter value is small d. Then how we actually calculate the metacentric height GM? So let us see here. So if you see, this is the axis of the cone. We have the axis of the cone. So if this is your axis of the cone, then in that case G will be somewhere here, M will be somewhere here, and B will be somewhere here. So if you see, this GM calculation is equal to BM minus BG. Okay, so this is the case. GM is equal to BM minus BG. Now if you see carefully, this angle, let us suppose this is theta. If this is theta, then apex angle means the angle made by this apex is 2 times of theta, because apex angle is the total angle of the cone, and this we are assuming to be theta. So they are asking, if specific gravity is of this cone is 0.8, okay, then what and can float in stable equilibrium in fresh water. So this is fresh water and this is cone material. So under what value of, what should be the minimum value of this 2 theta such that this cone remains in stable equilibrium? That's what they are asking you. Okay, now first of all, can you tell me, if this is the total height of the cone, can you tell me what is this distance? If this capital H is the total height of the cone, can you tell me from base what is the depth of centroid from this? So please tell me, if you take a solid cone, then from the base of the cone, what is the depth of the centroid of the cone? So please tell me this. All of you, please type in the chat box. Tell me, what will be the value of this G from this free surface, from this surface of the cone? H by 4. Very good, correct. So it is H by 4. This centroid is at H by 4. So that means if this is the volume which is surrounded, then obviously this distance is also how much? This distance is also small h by 4, correct. So this distance is small, means if you take this distance is small h by 4 in that case. Okay, so this is small h by 4. Okay, now let us see how we calculate Bg and Bm values. So Bm, so to calculate Bm is moment of inertia about the submerged phase by volume. So what is the moment of inertia? Look, if you see the cone is submerged like this. If the cone is submerged like this and this is the water line, for example, if this is your water line, now if you project this surface, at the water line, if you project this surface on the water line, so you will see a circle, yes or no? If you take the cross section at the water line, then definitely this is a circle of diameter d. Okay, of diameter d actually here. So this is some diameter of, oh, I think it got hanged or something. Just a minute. Okay, it is responding. So see here, this is a cone of some diameter, this is a circle of some diameter d. Now if you see, this is the axis, means if you take the moment of inertia about this perpendicular axis, that means in top view you are taking the moment of inertia about this axis, yy. Okay, so y, for example, if you call this is the axis about which you take the moment of inertia, because at the water line interface, if you have a diameter d, then definitely this top view of this face will be a circle of diameter d, because it's a cone. And now if this is a cone, then in that case, when you take moment of inertia about this axis which is perpendicular to the plane, then in top view that axis looks horizontal, like this vertical. Okay, so what is the moment of inertia about this axis for this cross section? Pi by 64 small d power 4 divided by, what is submerged volume? The submerged volume actually in this case is, if this h is the submerged volume, submerged height, and d is the diameter, so 1/3 pi r square, which means d by 2 whole square into h, so 1/3 pi r square h. So if you simplify the things, we will get something like pi by 64 times d power 4 divided by pi d square h by, this is 3 4s are 12. Okay, so you can simplify this, 4 table and 3 table, so pi gets cancelled, so 4 table 16 times, 4 table 3 times, so total 3 by 16 times, this d square gets cancelled, d square times, so d square by h. This is the value of the cone. Now if you see, yes, this is area of projection, yes, means basically if you cut it at the water line, you are seeing what is the top view of that surface. Clear? So if you see, if you cut at this water line, then if you see the top view, this is nothing but the top view of this surface at the water line. Okay, so we are taking moment of inertia about this point, and this point means about this axis which is perpendicular to this point, so that point, that axis is nothing but this axis passing through the center. Correct? So now this is Bm. So what is this Bm? Let us try to understand. If you draw the axis of this cone, basically this line, so okay, so see here, this angle is theta, this is h, and this is small d by 2. Okay, so small d, let us say small d here, so this is small d value. So we can do one thing at the same time, if this is capital D and if this is capital H, total height of the cone, then you can write tan theta can be equal to, tan theta is equal to, from similar triangles, if you see this d by 2 by h, so d by 2 by h, which is also same as capital D by 2 by capital H. So this is what we have here. Okay, so capital D by 2 by capital H actually. So this implies this small h or small d, you can write d is equal to h times capital D by h is what you can write here. Okay, so because 2 gets cancelled, small d is equal to small h into capital D by capital H. So if you replace here, this is equal to 3 by 16 times small d square is equal to small h square d square by h square into this small h. Okay, so this is what you have here. Okay, so by small h. So if you simplify this, you will get h square, this cancels h times, so 3 by 16 times of d square by h square times h. So this is what you have here. Okay, so 3 by 16 times of d square by h square. Or if you see, since tan theta is equal to d by 2h, if you make one 4 here, if you write one 4 here, 3 by 4 times of, you write one more 4 here, then this is equal to 3 by 4 times tan square theta times of h, small h. This is what you have here. Okay, so bm is equal to I by v, which is 3 by 4 times of this tan square theta into h. Okay, in case of triangles, a little bit I'm confused about projections. No, this is not projection, this is the cone actually which we are taking. Okay, so this value is the bm, metacentric radius value for this cone. So I by v is what actually have. So if you convert this, you have one h actually still left over. Okay, so this is 3 by 4 times of tan square h. Now what about bg? Bg is equal to, look, this is b, and if you take this distance, this is 3h by 4 obviously. Similarly, this is g. So if you take this distance from the bottom of the cone, this is 3 capital H by 4. So this bg distance is nothing but the difference between these two. So 3 by 4 times of capital H minus small h. Okay, so this is what you have here. Now if you simplify this, let us see what you have actually. Okay, and now if you see, weight of the cone should be equal to buoyancy force acting on the cone. So what is weight of the cone? Weight of the cone is equal to, weight should be balanced by buoyancy initially. Weight should be balanced by buoyancy, which means the weight of the cone, which is density of cone, g 1/3 by r square. R square means d square by 4 into h is equal to buoyancy acting on the small part is equal to rho, buoyancy acting on the small part is equal to rho of fluid g into the submerged volume, which is 1/3 pi d square by 4 times of small h. This is what you have. Okay, so now if you simplify this, 1/3 pi 4, 1/3 pi 4, g gets cancelled. So this implies density of cone divided by density of fluid. This gives you specific gravity of cone. So specific gravity of cone into d square capital H is equal to d square small h. So what we'll do here, specific gravity of cone is equal to d by d whole square into h small h by h is what you have here. Okay, so if you see, small d by capital D is equal to h by h. So if you write this relation, small d by capital D is equal to small h by capital H actually here. Okay, so we can replace this total value with small h by capital H whole cube. So small h is equal to capital H times of this specific gravity of the cone material whole to the power 1/3. So this is the depth of submersion of the cone into the water. Okay, so if you leave a cone, this h value up to which depth this cone will get submerged is given by this h into specific gravity of the cone material whole to the power 1/3. Okay, so let us substitute this h value in all the cases here. So we have one h, let us substitute all these cases. So therefore gm, metacentric height, is equal to bg, which is 3 by 4 tan square theta into h. 3 by 4 tan square theta into h. So what is small h? Capital H into specific gravity whole power 1/3 minus 3 by 4 times of h minus h, means h into 1 minus specific gravity whole power 1/3. So this value has to be positive now. Okay, because metacentric height has to be positive. So if metacentric height has to be positive, then if you see this 3 by 4 h, 3 by 4 h, this is constant. So this implies tan square theta in the limiting condition, equal to is also there. So tan square theta times specific gravity whole power 1/3 is greater than or equal to 1 minus specific gravity whole power 1/3. So this is the value actually. Okay, so from this you can get the value of theta, because specific gravity of the cone material is given. So if you simplify, you will get tan theta value. Okay, so it's very simple. Look, things, of course this is the explanation that I have given you. So if you see, you know, this calculation gm is nothing but metacentric radius minus metacentric height. So metacentric radius is I by rho. So I we have calculated for this circle. Where is this circle here? Missing. Why circle is missing? Circle should not miss. So okay, so let us suppose this is the diameter. Okay, so in that case, if this is the diameter, then okay, let us suppose I have drawn somewhere here. Okay, because this y axis yy should be visible. So if you see, we have calculated the metacentric radius, then we have calculated this bg value. So subtraction of these two should be greater than or equal to 0. Now how you will get the relation between small h and capital H? Because weight of the cone should be balanced by the buoyancy force acting on the cone. So if you see, this weight and buoyancy should be same. So if you match these two, you'll get small h value is equal to capital H times of specific gravity of the cone whole power 1 by 3. Okay, so did you all understand this? What we have done? We have done 3 steps here. We have calculated the metacentric radius, which is I by O, but of course for this D and H you need little trigonometry here. Second, we calculated this BG value. So because for this calculation of metacentric radius we need BM minus BG. Third, we need to know what is the value of small h. So we have known the value of small h in terms of capital H times specific gravity whole power 1 by 3. Okay, so if you simplify this relation is actually something like this. So tan square theta is greater than or equal to, tan square theta should be greater than or equal to how much we have seen? 1 minus sg whole power 1 by 3, 1 minus specific gravity whole power 1 by 3 by specific gravity whole power 1 by 3. Correct? Because if you see, we have specific gravity whole power 1 by 3. So if you simplify this, specific gravity of the cone is given, which is 0.8. Okay, so this is 0.8. So which means tan square theta is greater than or equal to how much? If you simplify that, 0.8 whole power 1 by 3, 0.8 whole power 1 by 3. So this is the value. This has to be subtracted from 1. Okay, so divided by specific gravity whole power 1 by 3 again. So if you simplify, this is the tan square theta value. Okay, so correct. So this is tan square theta value 0.077, 0.077. So what is tan theta from this? If you take a square root, this is the value of tan theta. So degrees tan inverse, if you see 15.53 almost. So 15 point theta should be greater than or equal to 15.53 degrees actually. Okay, so theta should be greater than or equal to 15.53 degrees. So apex angle is 2 times of theta. So when apex angle is 2 times of theta, so 2 times of this value is how much? If you simplify into 2, 31.06, 31.06 or 31.12, maybe some decimals they have, you know, rounded off something. So 31.12, which is in option D actually. Okay, so normally what happens, instead of taking complete values, if you take 0.76 to 2-3 decimals, then you might have got some slight change here. That's why we got 31.06 degrees. That difference is 0.06 degree, which is very minute. Okay, so of course it is answer D in this case. Is this clear to all of you? Did you all understand? It's not a very tough question, but at the same time you should solve this very you know, with patience, because if you make any one mistake, that's it, the answer changes. Clear? Solving this equation is easy, right? So did you all know how to use this virtual calculator to get these values of theta? So please type in the chat box, is this clear to all of you? Many times people have this misconception that they should take moment of inertia of the top view. No, because the top view cross section and the cross section at the interface, it means at the water line, both need not be same. Okay, so that's why if you see, always you should, if you see, I have projected the area, the cross section at the water line. I haven't projected like this, the complete surface. Okay, so always cross section should be taken, because normally what happens in case of rectangles and all, what they say, rectangle cross section remains same all over. So generally they tell you, you take the top view cross section and apply moment of inertia, but there the case is correct, because at the water line or at the top surface the cross section is same. But for solids like this cone or some other prisms and all, what happens, this area of cross section changes with depth. So in that case the water line cross section may not be same as the actual top view cross section. Okay, so that's why it's very, very important that you should always take the cross section at the water line. Is it clear to you? Is it clear to you? We have used calculator only at some last portion. Okay, but is this analysis clear to you for this cone? Yes? Okay, so let's go for the next question. Okay, answer is anyhow 31.12. yes, who has told 31.12? You know, Bhavya, all these people. Yes, you're correct. Okay, so let's go to the next question. So let us go to the next question. The uniform rod in the figure is hinged at point B. So there is a hinge at this point B. At this point B there is a hinge on the water line. Okay, so this hinge is to the water line. So if you see, there is a free surface of water that is present here. So there is a free surface of water at this location. Okay, so there is free surface of water and is in static equilibrium as shown. When 2 kg of lead, specific gravity 11.4, so lead is 2 kgs and specific gravity value is 11.4, are attached to its end. The specific gravity of the rod material is how much? Okay, and this is water, correct? So they have asked, this is what is the fluid? Water line. Okay, so this is water, then this is water. So they are asking you, if this block has to be in equilibrium, means if this beam has to be in at some equilibrium, at some angle, something theta is 30 degrees is given. So they are asking you, what is the density of this specific gravity of this beam material? Okay, so if you see the dimensions of the beam material, this is 8 meters in length, and of course specific gravity is actually given. Okay, uniform rod, so basically it has some diameter. Okay, so it has certain diameter value. Diameter is given. Okay, diameter is also given 4 centimeters. Good, diameter is given 4 centimeters. So it's very simple. Let us apply the free body diagram and let us evaluate. Okay, so if you draw the free body diagram, if you draw this free body diagram, then obviously if you see this is in water, so whenever this is in water, now let us calculate the total moments acting on this body. Okay, so the total moments acting on this body, the specific gravity of the rod material is dash. It's in static equilibrium. So first of all, can you tell me? Okay, so let us see. This is a solid. So now this is hinge B. This is hinge B. Now what are the forces that are acting on this beam? Actually, if you see, first of all, the weight of the beam acts exactly at the center. The weight of the beam acts exactly at the center. Weight of the beam. And similarly, there is weight of lead which is attached here. So this weight of lead will actually act here. Weight of lead. Now similarly, there is some buoyancy forces which are acting. So if you see, the buoyancy force acting at this location is F buoyancy on beam. And similarly, if you see the buoyancy force which is acting at this location, you have F buoyancy for lead. F buoyancy for lead. And of course, at this hinge, you have the reaction forces Rx and Ry, which pass to the moment center again. So Rx, Ry. So apart from these forces, weight of the rod diya hai kya? Yes, they have given you 2 kgs. Correct? So 2 kgs. No, weight of the rod is not given, but actually you need to calculate that only. Specific gravity of the rod material. Okay. So you don't know the density of the rod material. So let us try to calculate using this. Okay. Perfect, clear? Basically, you need to calculate the moment of inertia, specific gravity of this rod material. Okay, means indirectly you need to calculate the weight because volume is given to you. Okay, so let us see how we can calculate. So these are the forces which are acting at this location. Okay, and this is inclined at some angle. So this angle is theta. Correct. So if you see, this angle with horizontal for the beam is theta. So let us suppose this is theta. This angle is theta. If this angle is theta, then definitely this vertical, this with this horizontal also, the angle made by the beam is theta. Now let us see, these are the 4 forces which are acting here. Okay, so 4 forces about the moment O, about this point B is equal to 0 under equilibrium. Correct. So if this beam is in equilibrium, summation of moments about point B, considering counterclockwise to be positive, is 0. Okay, in this case. So if this is 0, then this implies counterclockwise moments. So if you see, counterclockwise moments are due to this buoyancy and clockwise moments are due to this beam. But before that, if you see, if you make a vertical, for example, at this location, if you make a vertical to this B, so let us suppose the length of the beam is L, then you know this is the centroid, So if this length is L by 2, then can I say this distance between these two verticals, means if you see this distance, which distance? This one. So can I say this distance is nothing but L by 2 cos theta? Correct? Can I say this? So let us suppose if beam is of total length L, then this length is nothing but L by 2 times of cos theta. Can I say this? Because with the horizontal this angle is theta and this height is L, this length is L by 2. Similarly, this total length is actually equal to L times of cos theta. Actually, L times of cos theta means these two forces has a moment arm equal to L cos theta and these two forces has a moment arm equal to L cos theta. Is this clear to all of you? So did you all understand this? The distance between this point of means this line of actions and this vertical, the perpendicular distance is L by 2 cos theta. Similarly here also this is L times of cos theta, correct? From this triangle, yes or no? Clear? Yes? So all of you should type in the chat box. Is it clear to all of you? Everyone should type in the chat box. Come on. Okay, now let us see here. If you add these moments, first of all, anti-clock moments are due to these buoyancy forces. So buoyancy force acting on beam into L by 2 cos theta plus buoyancy force acting on lead, buoyancy force acting on lead into L cos theta. So these are anti-clock. Next, clockwise, minus weight of the beam times weight of the beam times L by 2 cos theta minus this weight of the lead into L times cos theta, and moments due to these two reaction forces is 0 because they are passing through the moment arm. So this total expression is 0. So now let us see, this L into cos theta is common in every term. L into cos theta, L into cos theta. So L cos theta gets cancelled all over. Okay. So L cos theta gets cancelled. We'll see, Bhavya. We don't know. Let us calculate. Okay. So this gives you, if you simplify, buoyancy force acting on the beam by 2 plus buoyancy force acting on lead by 2 minus weight of the beam. Sorry, here 2 is not there, so here there is no 2. So buoyancy force acting on lead, because there is no 2 here. So buoyancy force acting on lead minus weight of beam by 2 minus weight of lead is equal to 0. This is the equation. So we want this point of interest, because if you see, out of these 4 terms, the main point of interest is this weight of the beam, because if you calculate weight of the beam, you can calculate the specific weight. Okay. So hydrostatic force लगेगा ना due to water. Yes, that hydrostatic force is basically this buoyancy force, correct? This is not a surface, Puffle, this is not a surface, this is actually some body. So on a body, when you keep in fluid, then definitely buoyancy is nothing but the hydrostatic force that is acting. Clear? So we have actually considered the hydrostatic force. Okay, clear, Puffle? It is not plane, it is a solid. Okay, so solid, so solids have this buoyancy force. Okay, so now if you see, what is weight of the beam from this expression? Weight of the beam is equal to 2 times of weight of lead minus buoyancy on lead minus 2 times of weight of the lead minus buoyancy on the lead minus buoyancy acting on the beam. Buoyancy acting on the beam actually. Okay, so now let us try to simplify that. Let us try to simplify this. So weight of the beam is density of the beam into area of cross section, means diameter is its diameter, so pi by 4 d beam whole square into g, L into g, so into length of the beam into gravity. So this is equal to 2 times of weight of lead, mass of lead is given directly, into g minus buoyancy force acting on lead is density of fluid times g into volume of lead. Volume can be written as mass divided by specific gravity. So mass divided by density. So mass of lead divided by density of lead minus buoyancy force acting on the beam is density of fluid into g into pi by 4 d square L. Now every value is given to you except this OC, because fluid densities you know. So let us suppose if you divide with fluid density, for example, if you divide this equation with fluid, okay, if you divide with fluid density, then directly you will get the specific gravity of this beam material. Okay, so rho beam. Okay, so let us write rho beam. So if you divide directly, density of fluid, here comes one density of fluid, then, and finally here comes this density of fluid. So this value is the specific gravity value. Okay, so you need to calculate the things. G gets cancelled all over, G is cancelled. So if you see one last expression for this value, what you have, let us see here. So let us bring one more page. Okay, so okay, fine. So if you see from this, if you see here from this expression, specific gravity of beam is equal to, specific gravity of beam is how much here? So if you see 4 pi by d square L into 2. So 8, total 8 is there. 8 pi by d square L, 8 pi by d beam square L multiplied with mass of lead by density of fluid, mass of lead by density of fluid minus mass of lead by density of fluid. One more, if you see, there is no density of fluid here. Okay, so this you have density of lead actually here. So divided by mass of lead divided by density of lead plus sorry, minus is there. So minus, you need to be careful when putting this plus or minus signs. So minus, then this pi by 4 d square L gets cancelled here. So pi by 4 d square L gets cancelled with this pi by 4 d square L when you divide. So this value is minus 1. Okay, so let us calculate what is this specific value. 8 pi diameter of the beam. So what is the diameter of the beam? It's given 4 centimeters in diameter, 4 centimeter diameter. So which means 0.04 square times length of the beam. So what is length of the beam? Total 8 meters length. So total 8 meters length multiplied with mass of lead. Mass of lead is how much? Mass of lead is 2 kgs. It's given 2 kgs lead. So 2 kgs lead. So 2 kgs divided by density of fluid. This is water. Specific gravities are given. So let us take water density, which is 1000 minus 2 divided by density of lead. Specific gravity is 11.4. So density is 11,400. This value minus 1. So let us simplify this. You will get the answer. Okay. So if you simplify 8 gets cancelled. So first of all, let us calculate this value. 2 by 1000 minus 2 by 11,400. Okay. So if you simplify this, you will get this value 0.001824 something divided into pi by 0.04 square into pi divided by 0.04 square. Okay. So if you simplify this, 3.582 and minus 1. So minus 1, if you simplify, you got 2.582. Is this correct? Did we miss some calculation anywhere? We are getting 2 point something. So please check this calculation carefully. So in this calculation, there is this 2 multiplication here, correct? So 2 multiplication. So 8 times by pi d square L. So 8 times 8 by pi d square L, correct? So 8 by pi d square L. So I think we have kept this pi in the denominator, but this pi has to be in the denominator, correct? So this pi has to be in the denominator. So this pi has to be in the denominator actually. Okay, this is the thing, because obviously if you see how I know my answer is wrong, because here if you see this value, the specific gravity of the beam should be less than 1. Otherwise what happens? The beam will sink. Okay, so that should not happen. The beam should float, which means the density of beam material should be less than 1. So whatever the answer we are going to get here, that should be less than 1. Okay, so let us check here. So if you simplify this, 8 by pi d square L is what you have here. So 8 by pi d square L. So if you simplify this expression once again, 2 by 1000 minus 2 by 11,400. So this value divided with pi divided with 0.04 square. If you simplify, this is what you have. So this value you have to multiply with. Okay, so please check in the chat box. Is this clear? Yes, did we consider all the terms? So once please check this. Weight of the beam should be equal to, so weight of the beam should be equal to 2 times of, this is inverse, correct? Weight of the beam should be equal to, so this is minus value and this is plus value, correct? Because if you see weight, if you send here, FB minus F lead remains as it is. So FB minus F lead should come here. So there is some minus and there is some plus here. Okay, so there is minus and there is some plus actually. So if you simplify, this is minus sign and this is plus sign. So this minus 1 and this is plus 1. So let us substitute these values. Okay, so if you see, this value has to be subtracted from 1. So if you subtract 0.637, okay, so this is 0.637 is the correct answer. So specific gravity of the beam material is equal to 0.637. 637 is the specific gravity of the beam. Okay, so yes, 0.638, 0.67, all these are within the range actually. Okay, so if you see carefully, this is simple moment analysis. So but you need to be a little careful with the plus and minus signs when you are shifting the terms on the equations. Okay, so if you see, we got a we actually made some mistake in the minus sign, so that's why our answer changed. But W beam, if you shift this side, buoyancy minus lead will be here, so minus of minus, buoyancy minus lead will be here, and this has to be plus. Okay, so similarly minus, plus, and minus, plus. So this calculation gave you 0.637 value actually. Okay, we have seen here, so this specific gravity is 0.637. Okay, so 0.637 is the correct answer. So let us check. 0.629 to 0.642. Okay, so which means this is 0.637. Clear? Okay, so how many of you got 0.67 along with me? So please type in the chat box. How many of you got 0.67? Everyone should type in the chat box. How many of you got 0.67 actually? If you apply this moment balance and you have calculated this 0.65. Done? Yes? Praful, Amit, Bhavya, Abhishek, Purnab, Neeraj, all of you guys. So hit. So type in the chat box. Got it? Yes. That's acceptable. Great. Okay. So fine. So 0.67. Acha, you have a doubt. Okay. Bhavya got 0.65. Yes, that is acceptable because if you see, range is in between 0.629 to 0.642. So that's why any value between this is acceptable. 0.65 is also acceptable. Clear? Okay. Great. So let's continue for the next question. So let us continue for the next question. So you see, gate ABC is a circular arc. So basically this gate, there is a water gate which is ABC. This is a circular arc called a tentagate. So basically what is a tentagate is, look, normally in fluid mechanics you might know. So there will be some adjustment in the screw so that this arms, if they want, they can, means at this location, so forces can be applied and this gate can be made more circular or less circular depending upon the tightening at this point O. Okay, so that's basically a tentagate. Okay, so let us see, is called a tentagate which can be raised or lowered. Of course, by pivoting at this point O, this can be lowered. See figure for position shown, the resultant hydrostatic force of water on the gate is dash kilonewtons. Okay, so they are asking you what is the resultant hydrostatic force on the gate. So see here, let us see, if you have this gate, for example, somewhere here, if you have this gate, if this is the axis of the gate, now what they have given you is, this is 6 meters. Okay, let me draw a dotted line. So this is 6 meters and this is also 6 meters. Okay, so these two sides are 6 meters and 6 meters. And 6 meters. Okay, and it's given clearly this height of water level is also 6 meters. Means if you see this point distance AC is also 6 meters. So if you see this distance is also 6 meters. Okay, so this height is 6 meters. So let us suppose if you draw like this, then let us draw the arc at this location. So because I want to make the arc look neat, so that's the reason. So this is the gate. Okay, so this is the gate. So this gate is A, B, C. Now what is the horizontal force acting on the gate? This is free surface. So if this is free surface of water, then what is the horizontal force acting on the gate? The angle 45 aega na to at O. No, let us see here. So if you see, this side is also 6 meters. Now this is point O. Now tell me, if you talk about this triangle OAC, this triangle is equilateral triangle, correct? If you see triangle at this triangle OAC is actually a equilateral triangle. Okay, so if this is equilateral triangle, can you tell me what is this total angle? Can you tell me what is this total angle? If this is an equilateral triangle, OAC is equilateral, then can you please tell me what is the value of this at O? Tell me what is the value at O? 60, correct? Because it's equilateral triangle, correct? So if it is equilateral, then this is 60. So obviously this here is 30. Okay, this is 6, this is 6, so this is 60, of course. So now let us see here, what is the horizontal force acting on the gate? So FH is equal to, look, let us suppose if you project this, if you project this, So if you project this, then can you please tell me what is the side view of the gate that you see? Let us suppose there is some width of the gate. Okay, width of the gate is nothing mentioned, so let us take unit width. So if you take unit width, then if the gate is like this, then if you see this in the projection, then can you please tell me what is the projection of this in perpendicular plane? Means if you take a plane like this, if you see it from this view, can you tell me what is the projection of this circular gate on this? So please tell me. It is rectangle, correct? So it is again a rectangle. So if you see, the projection is actually a rectangle. This projection value is rectangle. Okay, so this height is 6 meters and this is 1 meter. So 1 meter, this is 6 meters, and the centroid is somewhere here G, and this dimension is half of this 6 meters, which is 3 meters. Okay, so this is 3 meters. So if you want to calculate F horizontal is equal to density of fluid G into this area. What is the area? 6 into 1 into h bar, which is 3 meters, of course. So this is total 18 times density of the fluid into gravity. This is the horizontal force that is acting in the x direction. Now what is in the vertical direction? Fv is equal to, now this fluid is displacing this much volume of the fluid, yes or no, correct? The presence of this gate is actually displacing this much volume of the fluid. So volume of the fluid which is in the shaded region. So what is the volume of fluid in the shaded region? So first of all, what is this area? Density of the fluid times gravity into unit thickness 1. So this shaded part area. So what is the shaded part area? Look, you can calculate the shaded part area in this way. Calculate the area of total sector COA. From that, delete the area of these two triangles. Okay, these are right angle triangles, so delete this area. If you delete this area, then you can get the answer. Okay, so if you simplify, this total angle is 60 degrees. Okay, so 60 degrees divided by 360 into pi r square, which is pi times of 6 square, minus 2 times of area of this triangle. So what is the area of this triangle? This side is 3 and this side is 6, and the angle between them is 60. So half into 3 into 6. Why I am not putting 6? Because 6 is the total length, 3 is the half length. 3, 6, angle between them is 60. So sin 60, which is root 3 by 2. So if you simplify this, you can get 2 gets cancelled, 2 cancels this 3 times, this is 6, and 6 cancels this 1 time. So total the area is 6 times of pi minus 9 times of root 3, correct? So 9 times of square root of 3. This is the total area. Okay, the main art of this question is calculating this area. Okay, so if you calculate, let us see what are the values. They are asking you in kilonewtons, correct? So let us suppose, if you assume this density of fluid is 10 cube, water 10 cube, so Fh is equal to 18 times of gravity kilonewtons. So let us calculate this value. Similarly, this if you take 10 cube, then the value is 6 pi minus 9 root 3 times G, these many kilonewtons. So once you get these values in some kilonewtons, then F is equal to root of Fh square plus Fv square. Okay, so Fh square plus Fv square. So we'll see what is the value in kilonewtons. Okay, and they are also asking the values in kilonewtons. Okay, because they are asking in kilonewtons. So let us simplify the things. Okay, so 18 times of gravity, first of all, 18 times 9.81, 176.58, 176.58. This is your Fh. Fv, 6 pi minus 9 root 3, 6 pi minus 9 times square root of 3. So if you simplify this, 3.261 and multiply that with 9.81. So multiply this with 9.81. So if you simplify, 32, almost 31.99 kilonewtons. So almost some 32 kilonewtons. This is Fv. So Fh is known to you and Fv is also known to you. So let us calculate. Sorry, 179.45. 4 is what you are getting. Okay, final answer you are telling. Okay, let me check. Okay, so let us check. So square of this value plus 176.58 whole square, 176.58 square. So if you simplify this and take a square root, 179.454, 179.454 kilonewtons. Okay, so this is the total force, hydrostatic force acting on this curved gate, basically, which is the tenter gate. Okay, so if you see 179.45, so 179.4 is in between this two values, so 179.45 kilonewtons. Okay, so this is 179.45 kilonewtons. Clear? So all of you please type in the chat box. Is this clear to all of you? Okay. Look, it's very simple. We have actually calculated the horizontal force and also the vertical force. For calculation of vertical force, you need this area, means basically this volume of the fluid you need. So volume is nothing but this area into 1 unit thickness. So this area calculation is done in this way, that from the whole sector area we have deleted the area of these two triangles. Okay, so when you delete it, we get this area. So substituting this 6 pi minus 9 times of square root of 3. Okay, that's it. If you substitute, सर सर्कल्स का दोबारा बता दीजिए, ठीक है. I'll tell you. Look, if this normally, I'll tell you one thing. Let us suppose if this is circle. Let us suppose if this is center. If this angle is theta, for example, okay, then the area of this sector is theta by 360 degrees into pi r square. Okay, this is what you have, Amit. ठीक है. So now this sector is making an angle of 60 degrees, so that's why I have substituted theta equal to 60. Okay, clear? Is this clear to all of you? So please type in the chat box, is this clear to all of you? Okay, then let's go for the next question. Okay, fine. Next question. Okay, so let's go for the next question. So next question. So if you see a wooden beam, a uniform wooden beam is 10 centimeters by 10 centimeters. So it's a square cross section by 3 meters. Means if you see this length is 3 meters, but this cross section of the beam is a square. Yes, per unit se kiya aapne. Yes, I have done it for unit width. Okay, because width is not given, so for unit width I have taken. Okay, in that question. So let us see this question. A uniform wooden beam, specific gravity is given 0.65, is 10 centimeters by 10 centimeters by 3 centimeters. So if you see this length is 3 centimeters, sorry 3 meters, this length is 3 meters, and the cross section is a square cross section. Okay, so if you see the cross section, basically, so this cross section is, so this cross section is a square cross section. Okay, so a square cross section like this. Okay, so this is square cross section, means basically if you see this is a square cross section. Okay, so this is square cross section, and this is 10 centimeters. This is also 10 centimeters in dimension. Okay, now let us see what they are asking you. The beam will float in the water 20 degrees Celsius water. The angle theta, so this angle is given theta, which means basically with the horizontal, what is the angle made by the beam? This is what you need. Okay, so let us again calculate some things. So see here, you have the beam like this. You have the beam like this. This is a beam. Now let us suppose this is your hinge. What is the location of this hinge? A is given. A is given. Now water is till this particular portion. Okay, so water is till this particular portion. So water is till this particular portion. It's given. This height is 1 meter. This height is 1 meter. This height is 1 meter. And this angle with the horizontal is theta. This angle, the horizontal is theta. Okay, so if this angle is theta, then they have given you the specific gravity of the beam. Specific gravity of this is beam or what? Okay, beam, wooden beam. So 0.65. So wooden beam is given. This is 0.65. If this is 0.65, then let us see what is the value. Okay, so now if you see this beam, there are total 4 forces which are acting on this. So what are they? First, weight of the beam at the center. So weight of the beam at the center, W. This is G, weight of the beam at the center, G at the center. And now tell me one thing, if 1 meter is submerged, then remaining length is inside, so remaining volume of the fluid is inside, so definitely there will be some buoyancy force which is acting in the vertical direction at some location. Okay, so this is the buoyancy force. This is the buoyancy force, center of buoyancy. So this is FB. Now these are the two forces which are acting, and obviously the hinge reactions Rx and Ry will be acting. So, and this point is A. So under these conditions, this beam is in equilibrium, correct? So there are only two forces, beam weight and fluid buoyancy. So under these two conditions, the beam is in static equilibrium. So they are asking you what's the value of theta. Okay, so let us try to solve. So if you take again, for example, if you define some axis like this along the length, okay, so if you define some axis perpendicular to this length actually, so directly you know this length is how much? This is L by 2. So if you see here, so this length value, which length? This length value is A, for example, and let us suppose if you take this line, then this length value is B till this point. Okay, so let us suppose this length is B. Now if this has to be in equilibrium, at equilibrium, so if you see the perpendicular distance between these two, okay, so now you can observe, if you resolve this weight can be resolved like this. So if you resolve this weight as, if this angle is theta, then definitely this angle is 90 minus theta. So because if this angle is theta, this is the, okay, it is normal to the plate and vertical, so this angle is also theta because angle between two lines and their verticals is same. So this angle is also theta. So which means you have W cos theta and W sin theta along the base. So you have W sin theta along this base. W sin theta is what you have. Okay, similarly this F buoyancy, if you see that perpendicular distance between this buoyancy force and this point is actually this perpendicular distance. Okay, so let us see. Okay, let us not calculate B anyhow because B again will take some time. So let us not calculate B, we'll do in a different way. Okay, so this angle is theta, this much is known to you. Now this perpendicular distance along the length of the plate is A. Similarly, let us suppose the perpendicular distance between these two forces, between these two lines. Okay, so between these two lines here. Okay, so just a minute, something is happening. Okay, between these two lines is B, for example, B, this is B and this is basically B, and at the same time let us not resolve this also. So if you, rather than resolving this, let us do as a single force by taking about this vertical axis. Okay, by taking about this vertical axis, let us do it as a single value. Okay, so W sin theta, let us delete. Okay, so fine, this theta is not required, and this instead of this A, what we'll do, we'll take this value is actually A, this value is A, we'll take this. Okay, both are vertical forces, then why to again go for components? Okay, so simply this is simple because this coordinate system is very easy to analyze. Okay, so now sigma moments at equilibrium, summation of moments about that point A, hinge in the counterclockwise direction, is basically 0, correct? In the counterclockwise direction they are zeros. So in the counterclockwise direction, if they are zeros, so if you see this W weight is actually creating a counterclockwise moment and this FB is creating a clockwise moment, means W times of A minus FB times of B is equal to 0. Now let us calculate what are the expressions basically for all these four coordinates. Okay, so WA minus FB is equal to 0. So W, weight of the beam is equal to, look, specific gravity is given, dimensions are also given. Okay, 10, 10 and 3 centimeters. So weight of the beam is equal to density of the beam into gravity into volume. So 10 centimeters by 10 centimeters by 3 meters. So this is the density of the this is weight of the beam. So density can be multiplied with 0.65. If you multiply with 1000, you will get 650. So 650 times G times 0.1 into 0.1 into 3. So this is W value. Okay, now what is buoyancy force? This is important actually. Okay, so buoyancy force is equal to, look, what is the buoyancy force value? See, if this is 1, then definitely this is 1 by sin theta, correct? So this value is 1 by sin theta value. Clear? So this length along the beam is 1 by sine theta. 1 by sine theta. So this is this length of the beam, okay, because if this is 1 meter, then this is 1 by sine theta, and this is the water surface, which means the volume of the beam which is inside the fluid is equal to area of cross section into this balance length, which is 3 minus 1 minus sine theta. Sorry, 3 minus 1 by sine theta is what you have here, okay. 3 minus 1 by sine theta is this value, and this is 1 by sine theta value, okay. So FB is equal to density of the fluid times gravity into density of the fluid times gravity into 0.1 into 0.1 into this length, which is 3 minus 1 by sine theta. This is the case, okay. So this is the FB value. So you have W and also you have FB. Now what is small a? Small a is equal to, look, this total length is L by 2, okay. So total length is L by 2, and if this angle is theta, that means if you see this angle is also theta, so this small a is L by 2 cos theta. L by 2 cos theta is the total value. Now what about this B? This is what you need to calculate, okay. So B value is equal to, so B is this value. Look, first of all, if this total length is 3 minus 1 by sine theta, then this length is going to be half of this total length, correct? So let us suppose from the total length, if you subtract this part, you will get this value. So cos theta of this remaining part gives you this dimension, okay. So if you see, B is equal to, so basically what is B? B is equal to out of all these terms. So first of all, let us subtract this value. So if you subtract this value, 3 minus 1 by sine theta by 2. So half of this value, if you subtract from 3, then you will get this portion BA. So that value into cos theta, okay. So this value into cos theta actually gives you this value. So you have W, FB, A, B. Let us substitute here. So W into A, which means 650, G 0.1, 0.1, 3 into A, which is L by 2 cos theta, which is 3 by 2 cos theta. So this value is equal to this density of the fluid, which is this buoyancy, which is density of the fluid into G, density of the fluid, G 0.1, 3 minus 1 by sine theta, 3 minus 1 by sine theta into, look, if you simplify this, if you take LCM of this term, 2 times of 3, 6 minus 3, so you have 3 plus 1 by sine theta by 2. So this is 3 plus 1 by sine theta by 2. So this is the value actually. So this is the equation which you need to, yes, trigonometry we need to use actually here carefully, okay. So if you use trigonometry carefully, that's it, you will get the answers, okay. So now if you see, let us calculate some common terms. 0.1, 0.1, 0.1, 0.1, G, this density of fluid 650, this gives you 0.65 here. Next, anything that can be cancelled more, okay, cos theta, and this cos theta also comes here, so cos theta is also there, so cos theta and cos theta gets cancelled out, okay. So this implies 0.65 times 3 into 3 by 2, 9 by 2 is equal to, here if you see, 3 minus 1 by sine theta into 3 plus 1 by sine theta by 2. So A minus B into A plus B form. So 9 minus 1 by sine square theta by 2 is what you have. 2 gets cancelled here, okay. So now let us simplify the value of theta from this equation. So from this equation, what is the value of theta? So 9 minus 9 into 0.65. So this is equal to 9 minus 1 by sine square theta is equal to 9 minus 9 times of 0.65, means 0.35 times of 9. So sine square theta value is 1 by 9 into 0.35. This is the value of sine square theta. So sine theta, so sine inverse if you keep degrees, 34.3 degrees, 34.29 degrees is what you have in place of this theta, okay. So this is how, this is the angle at which, concept is the calculation length. Yes, of course, calculations has to be done because such kind of questions can be asked. If you see, there are only 4 things, okay. The only thing is you need to take little help of trigonometry, otherwise equations are simple. See what we have done, 2 lines, actually 2 lines we have, but identifying this is 3 minus 1 theta takes little visualization actually, okay. So it takes you some little help of trigonometry. Clear? So once that is clear, we can, we can easily identify this 34.29. So what is the angle? 34.2 is actually in between this. 34.29 is exactly the value. Range is given 34 to 34.58. 34.29 is exactly middle value of this range. Okay, so 34.29. See, you need to calculate these kind of realistic examples here. Not like, I'll give you some, for example, something like there's a cube, 40% is in mercury, 50% is in. These kind of questions, okay, they're very easy, you can solve them. But when you try to solve these kind of realistic questions, it's obvious. If you see, if you leave a beam, it will float. What is the angle? So when you solve these kind of questions, it creates some interest in you. Okay, so that's why if you see. But of course, calculations, you need to take care, trigonometry and all. So after calculations, you see, we directly get the values. Okay, 34.3 is the correct answer. Okay, so if you see, this beam is floating actually. So when this beam is floating, this angle of equilibrium is 34.29 degrees. Okay, clear? Yes, 34.29 is correct answer. Okay, 34.29 is correct answer. So let us calculate the next question. A cube of side A float with one of its axis vertical in a liquid of specific gravity SL. If the specific gravity of the cube material is SC, the sum of possible values of SL by SC for the metacentric height to be 0 is dash. For the sum of possible values of this ratio SL, specific gravity of liquid by specific gravity of the cube, for the metacentric height to be 0 is dash. So first of all, let us see if cube is floating. This is a cube. So let us suppose this is a cube. So this cube is floating. This cube is floating. Okay, this cube is floating like this. So what is this height of submersion? H. For example, let us suppose this is the depth of submersion H, and this total value is A. For example, it's a given a cube of side A. Okay, so this is A. This is also A. This is also A here. Okay, if this is also A, now definitely if you take the centroid will be at this location G, and buoyancy will be at this location. So if you see, this is H by 2 and this is A by 2. A by 2. Okay, so first of all, let us calculate what is H. So weight of cube is equal to buoyancy due to liquid. Buoyancy of liquid, you can calculate buoyancy of liquid. So if you equate this, density of cube into G into volume of the cube is equal to density of the fluid into G into, now what is the volume that is submerged? If you see, this height is H, but the base is A square, because a cube has constant base of a square. So that's why if you see, this cube has a square cross section, so A square is as it is multiplied with this H, so A square into H. Okay, so if you simplify, obviously A square cancel this A times, G cancels. So now if you see, if you divide this density with water on both sides, this is nothing but specific gravity of cube into A is equal to, this is specific gravity of the liquid which is present here, into H. So this implies H is equal to A times of SC by SL. So this is the value of height H which is submerged in the cube. Now if you calculate the metacentric height GM, metacentric radius minus this BG value. So what is this metacentric radius? BM is equal to moment of inertia about YY divided by the submerged volume. So what is IYY? Look, at this water line, if you take this cross section, that is A square. So A power 4 by 12 directly into volume submerged, A square into SC by SL times A, because this H value, A square into H is the volume submerged, H value is A into SC by SL. Okay, so SC by SL. So if you simplify this, A square and A cancel this, A times, so this is we can write SL by SC, SL by SC times of A by 12. Okay, so this is A by 12. And what about BG? BG is how much? A minus H by 2, because if you see from this base, this is at A by 2 and this is at H by 2, so the difference between them is A minus H by 2. So if you simplify, A minus H by 2, so 1 by 2 times of A, if you take out, then 1 minus H by A. Okay, so 1 minus H by A. So what is the value of H by A, SC by SL? SC by SL. Okay, so this is what you have here. Okay, so this is A by 2 times of 1 minus SC by SL. So GM is equal to 0. This means this metacentric radius should be equal to the difference between centroid and center of buoyancy. So BM is A by 12 times of SL by SC is equal to A by 2 times of 1 minus SC by SL. So what are the values they are asking you? Sum of possible values of this SL by SC. So let us take this value as X, for example. If you take this value as X, for example, then this equation is something like, if you cancel, A gets cancelled, this is 6. So this implies, if you take this SL by SC as X, X by 6 is equal to 1 minus, this is 1 by X. Okay, so 1 minus 1 by X. So let us suppose if you simplify this, then X by 6 plus 1 by X is equal to 1. So if you simplify, X square minus 6X plus 1 is equal to 0. This is the equation. So please tell me, first of all, if this is the ratio of SL by SC, specific gravity of the liquid by specific gravity of solid, this this cube, then tell me this is a quadratic equation. Now you know, if you solve this, you will get two values. So can you tell me, if you solve the roots of the quadratic equation, what is the sum of the roots for this equation? Can you solve this quadratic equation? So if you solve this quadratic equation, can you tell me what are the roots of this equation? So please tell me, what are the roots of this equation? Sorry, what is the sum of roots of this equation? Obviously, if you have this equation, you know, ax square plus bx plus c equal to 0, sum of the roots is equal to minus b by a. Okay, so this is what you have, minus b by a directly. But normally, so that's why if you see sum is equal to 6. But okay, mathematically sum is 6, but we need to be very cautious about one point. Let us suppose when we solve this quadratic equation, let us suppose one value of x is negative, then is that negative value possible value of this SL by SC? Because when you solve a quadratic equation, definitely there could be some negative values also. So whenever the quadratic equation is solved, if you get negative values, then are they possible? If you have some negative value, is the negative value a possible value for SL by SC value? No. Okay, so here when writing this equation, we need to be very sure that both these values of x are positive. Okay, so let us calculate. Of course, using minus b plus or minus, all these things you can calculate, but since you know we have some quadratic solvers directly, I'm using this quadratic solvers. Okay, so quadratic equation solver I'm using directly, because you can generally calculate roots of a quadratic equation very simply, but let us suppose I am solving this. Okay, so first coefficient is 1, this second coefficient is minus 6, and third coefficient is 1. Okay, so x square minus 6x plus 1. So if you see, the roots are 0.171 and 5 point, correct? What we have got is correct. It should be minus 1, no? Minus 1 is equal to 0. Okay, this should be minus 1. 6x minus 1 is equal to 0. Okay, now both the values of x should be more than 1 also, because if you see SL by SC, normally this cone, this cube will float in this liquid only if this value is greater than 1. Density of cone should be, density of this cube should be less. Okay, so this value has to be greater than 1. Let us check if values are greater than 1 or not. So here if you see this value, this is minus 1. So if this is minus 1, then x square minus 6x minus 1 is equal to 0. Okay, so if you see, we got the root something like this, x square if you see x square, this is plus 6, no? Correct? I'm sorry, we are making some calculations here. So this is plus 6 is equal to 0, correct? Because if you see x square plus 6 is equal to 6x. Okay, so let us take plus 6 in this quadratic solver. So plus 6. Okay, so if you take 6 value here, you see both the roots are actually positive. Okay, both the roots are positive, 4.732 and 1.267, and both values are more than 1. So these two values are possible for this equation. So we can undoubtedly say this is 6. What are the possible values of x? X is equal to, if you solve, we will get 4.732 as one value. Normally you can calculate quadratic equation roots. Okay, you can take minus b plus or minus root of b square minus 4ac, all these things, but I'm just writing. Why to spend some time? We all know how to solve quadratic to 1.268. okay, so 1.268, since both these values are greater than 1, okay, both these are permitted for this value to be greater than 1, means under these two values of this SL by SC, the metacentric value, the metacentric height of the system is actually 0. Okay, so these are the two possible values. Since these two are valid, so we'll take sum of these two, which is 6, which is nothing but roots of this quadratic equation. Clear? Are you all enjoying the questions? Can you definitely find some questions? You might have seen some of these questions in some standard books like Frank and White. Few questions I have taken from Frank and White unsolved. Okay, some questions I have taken from Sengel unsolved. Okay, so you might have seen these questions, but you might have, you know, got very much in trouble to solve these questions. Are you all feeling comfortable now? Fine. So please type in the chat box. Are you all experiencing some good questions using all the concepts mathematically, physically? Okay, all the things. Are you applying here? Curved surfaces we have covered. Okay, plane surfaces we have covered. We have covered some some concepts of buoyancy, concepts of meta center, all these things. Okay, so definitely, if you, I'm telling you, as I promised you on day 1, if you can solve all these questions in line with me, then definitely you will have all the knowledge set that is required to solve GATE 2023 questions. Okay, so once you solve these questions, definitely you can solve GATE 2023 questions. Okay, now let us go for next question. Okay, this is 9 questions. Still, how many questions we have approximately? Okay, we have 2 more questions, but fine. Okay, let's see what happened. So let us suppose this is a gate. Okay, there is a gate like this. A rectangular gate of L is equal to 1.53 meters. So this length of the gate is 1.53 meters as shown in figure. As water rises on the left side of the rectangular gate, then the required depth for gate to open is dash meters. Neglect mass of the gate, assume atmospheric pressure on both sides and no friction at hinge. So this is your hinge. So if you see, this is your hinge. So they are asking you, don't assume any friction at the hinge. Okay, so now if you see, if you draw the free body diagram of this, first of all let us try to understand the physics that's happened. So first of all, as water level increases, definitely hydrostatic force on this vertical face increases. Of course, hydrostatic force on this horizontal plate also will increase, because as this liquid level is increasing, the pressure at this location will also increase. But at one particular location, definitely the hydrostatic pressure on this vertical portion will exceed the hydrostatic moment due to this horizontal plate, and this plate will actually take a, means if this is the plate, this plate will actually take a turn about this hinge. Okay, so because of the hydrostatic force acting on the vertical face, the moment, when the moment of the force acting on the vertical plate is high, then definitely this plate will definitely take a rotation and the gate will open. Correct? So when gate will open, fluid will fall over this. Okay, so let us see free body diagrams. Okay, so free body diagrams, let us suppose if you see the free body diagram, the gate is like this. It's a rectangular gate kind of thing, cross section is rectangular. So let us suppose if there is a gate like this. This is the gate. Okay, so this is the gate. Now here, you know, definitely the water level is D. The water level here is free surface, and this is D, for example, to this hinge, and this length is given 1.85 or 1.58, something is given 1.53. Okay, 1.53 meters. 1.53 meters. Okay, look, 1.53 meters. So if you see, there is definitely certain increase in the pressure like this. Increase in the pressure. So there is some increase in the pressure like this. So if you see, pressure will actually increase. Okay. Pressure will increase. So whenever this pressure is increasing, obviously, you know, there is this complete effect of the pressure can be replaced with one single force, which is the hydrostatic force, FH. FH. Okay, FH. Now similarly, on the bottom face, if you take on the bottom face, you have certain uniform hydrostatic force, because this plate is horizontal. So if you see, the hydrostatic force acting on this plate is uniform. So like this. So if you want to replace this complete force with a single force, then exactly at the midpoint you can replace this. Okay, so now let us suppose the width of the plate into the board is W. Let width of the plate is W. Let width of the plate is W. Okay, then definitely you know this center of pressure is how much? H star value is equal to 2d by 3, correct? Because if you see in case of rectangular plates, let us suppose if this is the depth which is submerged, then the depth of center of pressure from the top surface, from the free surface, is 2d by 3. We have calculated this value. If you remember, if this is the surface, if you have a rectangular plate like this, if this dimension is h, then we have shown in the, means basically you might know this. Okay, I didn't tell you, I was teaching in the Prakam batch, sorry. Okay, I didn't teach you, but you might have known that if this is the center of pressure, Cp, then this value is 2h by 3, correct? If this is 2h by 3, but the rotation is about this hinge, okay? So what is this length? H by 3, okay? So this force is having a moment of F into h by 3, okay? Next, about this location, if this value is equal to L, for example, this is L by 2. So let us see what is the total forces acting, Fh and Fv, let us say. Then the moment due to at equilibrium, what should happen? This moment which is topping the plate should be counteracted by this Fh moment. So Fh times of d by 3 is equal to Fv times of L by 2. Okay, if this is the total length L, then exactly this length is L by 2, so you can have a moment. So what is Fh? Density of the fluid times G into area of the contact, area of wet surface, D into width of the plate. Okay, so D into width of the plate into rho G A into H bar. So what is H bar? D by 2. Okay, depth of centroid directly H bar D by 2 into D by 3. This value is equal to F vertical. So F vertical is nothing but, if you see this pressure, this point is at a depth D from the free surface, so actual pressure is P atm, but because of the P atm here, if you see the static pressure at this point, effective static pressure at all these points is rho GD. So rho GD multiplied with the area. So what is the area here? Length into width, length into width into L by 2. So this is what you have. So if you simplify the things, we have 2 gets cancelled. Okay, rho Fg and rho Fg gets cancelled. Of course, this is also fluid. These two gets cancelled. One D gets cancelled. W gets cancelled. So what you have basically D square by 3 is equal to L square. So D is equal to root 3 times of L. Okay, so D is equal to square root of 3 times of this length. So what is this length actually here? So square root of 3 into length. Length is how much? 1.53 is given. So this many meters. So let us simplify this. Square root of 3, 1.53 into square root of 3. Okay, 2.65. 2.65 meters is the actual value of D at which this gate will actually take a rotation. Yes, 2.65 is correct. Okay, so 2.65 is the value, correct value. Option A, answer A, which is here. So 2.65 meters is the water level at which this gate will, rotate about the hinge. Okay, clear? What about PATM on right side? Look here, this PATM effect is cancelled. At the same time, right side also, on the top there is atmosphere. Like this there is PATM, and here also it is PATM. So that's why this pressure at this point is just taken as P, this difference, because actually the pressure at this location is P naught PATM plus OGD. But since PATM is also in the opposite direction, the net effect is due to the pressure component OGD. Okay. Yes, PATM will actually get balanced on both sides, of course. Clear? So is this clear to you? So please type in the chat box. Did you all understand that PATM gets cancelled on both sides of the plate actually? Okay. Yes. Fine. So basically these concepts of buoyancy and flotation is a bit very nice concepts actually, and I hope in this session you might have got some new points. Definitely meta centers, this solids like cones, rectangles, all this square, cubes actually. Okay, so cubes, we have talked about all these things. We talked about hydrostatic forces on some curved surfaces like the dam question, this Tainter question. We have talked about some curved surfaces, hydrostatic forces, and we have done this plane surfaces also. You remember, center of the plate is applied with a force F. Okay, this is also some plane surfaces kind of question. Okay, we have dealt a lot of buoyancy questions. In case of fully submerged, partially submerged, we calculated metacentric heights, all these things. So generally these are the type of questions, and two very common points that I would like to tell you. In case of completely submerged bodies, center of gravity should lie below the center of buoyancy for the body to be in stable condition. Okay. Whereas in case of floating bodies, this concept of B and G alone cannot decide the stability of the bodies. So we go for one very important concept, which is called meta center of the bodies. Okay. So that's meta center is basically the point about which the body actually rotates. Okay. So that's how we calculate this meta center. Okay. So I hope you all liked this session. You got some very new some nice questions actually and some good points. So if that's fine, then we will say one formal thing which is here. So thank you, that's it. Okay, so clear to you? So please type in the chat box, is this clear to all of you? Very important thing is, when calculating hydrostatic forces, your mind should work very quick with trigonometry. Okay, because identifying some lengths is of main importance. Okay, moment arms, all these things is important, so that's why you need to work it out. Okay, fine then. Okay, so thank you all. We'll meet again tomorrow at 11 AM with very good questions on differential analysis of fluid systems. Okay, so we'll talk about this, basically kinematics, all these things we'll talk about tomorrow. So that's why we'll talk about this differential analysis of fluid systems basically. Okay, so we'll solve some again good questions there. Okay, clear? So tomorrow's session is more like mathematical, because you see from kinematics we'll start solving some equations and all analysis, so things look more, of course even though we have equations, but more differentiations, derivatives, all these things comes out. Okay, so thank you all. Thank you. If you have any issues, you can talk to me, you can ask me, or else it's fine. We'll close this session. Okay, fine then. No questions. Okay then, take care, bye. We'll meet tomorrow at 11 AM. Thank you all. Thank you.